So over the past couple of days, you've learnt a bit about the science and mathematics behind climate models. Now we're going to take a bit of a look at how they're implemented, how their outputs are analysed, and how we share data both within the centre and to the outside world. Climate models are a complex community effort created by many people of various different specialities working together. So this is only going to be a high-level overview for this presentation. Certainly we could probably do an hour worth of presentation on each of the slides here. Models can vary dramatically in complexity from something simple enough that you could just calculate it by hand with a bit of pen and paper and some patience, to huge numerical weather prediction systems that take a day of compute time to model, or take a day of compute time to simulate a day or two of the actual weather. Oops. Got this? No, we'll get it working. Next. Let's try this. Here we go. Climate models work by solving a discretised version of the Navier-Stokes equations. So by discretisation, we mean we're breaking up the true continuous field that happens in the actual Earth's atmosphere and representing it on a grid that we can actually store in computer memory. There's a range of different options on how the equations of motion can be discretised. The finite difference method is what's most commonly used in numerical weather prediction systems. There are some systems, though, that are starting to move towards finite element solvers, which is a different way to solve the equations of motions. So the ELFRIC model being developed at the UK Met Office is one of those. So a simple way to discretise the equations of motion is just a regular grid in latitude and longitude, like you can see on the left there. As model resolution increases, however, you get an artefact happening at the poles where all of the grid points converge to a single point. So right here, we've got really, really tiny grid cells. So we're spending a lot of compute time. We've got to drop down the time step to get the equations being solved properly on this tiny area in the centre of Antarctica that we're not so much caring about. So this discretisation process doesn't just work with the spatial domains, so we're not just lat and long, but we've also got time. And as we lower the time resolution, we also have to, or increase the time resolution, we have to lower the temporal, increase the spatial resolution and increase the time resolution correspondingly. To reduce the impact of the grid poles on the models, as we're moving to much higher resolutions as exascale computing, models are starting to move towards alternative grids which avoid this issue at the pole. So on the left, we've got a cube sphere grid. So that's fairly simply constructed. You've got six regular grids, and you've joined them, stitched them together to form this sort of cube sphere. So rather than having the vertex where all of the whole latitude dimension is converging, here we've only got 3 points converging. So that's much better behaved. This is being used by the ELFRIC model. It's also being used by GFDL's next generation models. On the right, we've got another different type of grid. This is using something called a Voronoi tessellation. So this is constructed by distributing points around the grid, around the globe, and then the area of each grid cell is the closest points to those generating points. So that allows for a regular-ish grid that's also, you can vary the resolution around the globe. You can focus in on a specific area of interest. It does come at the cost, however, of increasing the complexity of solving the equations. For an ocean model, on the other hand, they don't really have the same problem that a whole globe atmosphere model would do, because they can move around the poles where they like. So on ocean models, you tend to find, rather than a pole at the geographic north and south pole, you have one pole at the south pole, where it's Antarctica, it's not ocean, they don't care. And you have other poles in the middle of North America and over Eurasia. So you end up with a tripolar grid, and there's a mapping to construct that over the globe. So also when solving the equations of motion, we tend to use a staggered grid. So by that we mean that the vector components of the fields, so like your wind fields, your U and V, are on different grids to the scalar components, so like temperature. And that basically just increases the stability of the equations. So it allows you to use a larger time step for the same accuracy. It's also less common nowadays, but you do see models that use spherical harmonics, spectral methods to solve the equations for motion. So I think Todd covered this a little in the first lecture of the week, where you're basically decomposing the fields on the globe into spectral decomposition. The reason they're not so much used nowadays is they require fast Fourier transforms to switch between real space and spectral space. And as you're increasing the number of processes, that really increases the number of communication. They don't scale very well when you're moving to high resolutions. So the fields on the grid are represented in the model in the computer itself by using a multidimensional array for each field, which stores the value at each of our grid points in our decomposition. So starting off simple, let's look at how an individual computer works, like would be on your laptop or on your desktop at home. We've got two primary components. We've got a CPU and we've got memory. And basically the computer works by grabbing data from memory or disk. Disk is effectively memory for the case here. Loading it into registers and then grabbing a bunch of instructions, which is your computer program. That gets loaded into a computer core. So cores, what's a good way to say this? So the core, CPU, a single computer can have multiple cores, and they can each run a program at the same time. So that could be, so you can run multi-processing basically. So you can have one program running on one core and a different program on the other core, or you could split a program and have it running across both cores. So yeah, the program instructions get read by the core, the data gets read into things with funny names like XMM1 is one of the registers on the processor. There's only a couple dozen of these, so your computer can't work on a massive amount of data at once, but it just loads data in, operates on it, then stores that data back out. The largest of these registers is going to hold about 512 bytes of data, which is about 64 values for a double precision array. So the program reads a list of instructions on what commands to run from the memory. So this is going to be your program. So if we wanted to add two arrays in our program, here's a Fortran program that would do that. So we see we've got a couple inputs arrays, an output array, and just looping through. So that gets compiled by a program called a compiler, funnily enough. So that converts this human-readable program text into something that the computer can read. So on the right, we have assembly. This is still sort of human-readable. It's not what the computer directly sees, but each one of these words gets converted to a number that the computer can understand. So it gets converted into special instructions. So here we've got two types of instructions. Move-ups will load data from memory, from our first argument, which was A, into a register. Here it's loading it into XMM1. those argument B into X and M naught, then runs an add instruction and stores the output by copying it back out. So that's basically how the program runs. Interestingly to note here, on the left I've looped over 4 values, but on the right that doesn't happen. The compiler has automatically optimized it because these values are continuous in memory. It can load all of those values in the same operation. So it's really important to think about the layout of your data. If you've got continuous data, the computer can do operations like this where it's optimizing things by loading a bunch of data at the same time and working on all of those values. So there's lots of optimizations that computers can do like this. Generally, it's best to leave low-level optimizations to your compiler, or if you're using Python, the interpreter works slightly differently, but effectively the same. Just leave low-level optimizations to the compiler and don't worry too much about really digging in and optimizing things like this. So we've seen to solve the Navier-Stokes equations, we are discretizing the equations of motion. So each field is getting represented by a multidimensional array, and we can do optimizations if we loop over things in the right order. So memory in a computer is not 2-dimensional or 3-dimensional or 4-dimensional like our data fields. Memory in a computer is 1-dimensional. So the compiler has to change our layout in our array, in our program representation, where we've got sort of a 2D representation, and create a 1-dimensional array out of that. So in this case, we've got a 2D field, and the compiler has chosen, the way it chooses depends on the program language you're using. So this is for Fortran. It's chosen to grab all of the first column and lay that out continuously in memory, and lay the second column out, and then the third. So we want loops in our program if we want our continuous data that we can optimize to go over the column first. So yeah, accessing data from memory is going to be much faster if they're close to each other in memory space. You can see sometimes in models there's strange ordering of values to make best use of this. So for WRF, for example, the arrays are in dimensions of latitude, then level, then longitude, rather than what you might naively think, so level, lat, long. So that allows them to always have the latitude loop as the outer loop and the longitude loop as the inner loop, which is increasing efficiency for them. So modern climate models are too complex, there's too much stuff in them, and too high in resolution to be able to be efficiently solved on one computer only. So depending on the complexity of the model, they're going to be using from as little as a few cores to thousands, which is getting into the domain of supercomputers. So let's take a look at how that all gets coordinated to properly solve the equations of motion. So supercomputers, like NCI's Raijin, are basically a big bunch of normal commodity computers like you'd find on your desktop, collected together into a data center with a really fast network connecting them all. So a node on Raijin, where we have like a compute node or a login node, is effectively one of those desktop-ish computers. And Raijin has about 4,500 nodes altogether. So there's the really fast network connecting them all is called InfiniBand, so it's like fiber optic and stuff. Most supercomputers will be structured reasonably similarly to Raijin. We've got two types of node, the login node, That's where you connect to when you connect to Raijin. There's only a couple of these. And then the bulk of the nodes will be the compute nodes where jobs actually get run. So to get your job from the login node to the compute nodes, you have to submit it to a queue. And that's allowing jobs to be efficiently shared between different users on the system, making sure that the system stays utilised. These cost a lot to run in energy, really. Power is the limiting factor in how big your supercomputer can be most often. So they want to make the most of that energy. So in addition to the general purpose nodes, Raijin's got a bunch of storage systems for various uses. We'll get into them later. And also a special data mover node, which you can use to copy data into or out of the system. So we've got the equations of motion on a grid which the computer can deal with. But how can we make the best use of the supercomputer? A simple way to do this is to break up our grid. So each of the nodes is going to be running a different part of our model. So we split up our full global domain into a bunch of smaller things, and each of one of those is going to be run separately. So we want each of those processes to be doing approximately the same amount of work. So we want them to finish at the same time. We don't want 8 of these processes to all be waiting, doing nothing, while a single one is trying to progress. So we want these to be roughly equal in size. That's easy for an atmosphere model. It gets more complex for a land or ocean, where you're not actually covering the whole globe. So for a regular grid, we can split the full domain into rectangular subdomains. With some operations, like gradients and things like that, they don't just need a single grid point. They need an area around them. So for that, we need to get data from the neighbouring processes. So this one, if we want to calculate the gradient across this boundary, we need values on both sides. So there's a couple of different ways that we can do that. There's 2 main methods where nodes share workload. On the left, we've got shared memory. In this case, each process, each core on the computer can see the whole data set. Obviously, so that's going to share memory. It's depending on how it's set up, that can either reduce the total amount of memory. It keeps the same amount of memory because you just store it once and all of the nodes access that array. Or if each one gets a copy of that, that's obviously going to increase the memory. The other way is distributed memory. So that's where each of the compute processes only has its one bit of the picture, but they're going to communicate using that InfiniBand network, using NPI message passing, communicate the data on the boundary so they can calculate their gradients or etc., things like that. In shared memory, each of the individual processes has access to all of the program state. So if we want to loop over a field, we can just loop over the entire field. We just have to add an annotation to the top, which tells the compiler that this is going to be a shared memory loop, and it automatically splits up the loop over the array to the different processes and parallelizes it for us. So this is just a basic heat equation solver. We're reading from a bunch of different neighbour cells, so we're reading from one to the right and one to the left, and the parallelization automatically handles that for us. It is a bit more complex because we have to be careful that we're not writing from one process to an area that another process is reading from. So we've got to be careful of ordering when we're doing things like that. So historically, there have been whole supercomputers built around this model where there's just one memory shared by every node of the supercomputer. That's less common now, so you don't tend to see whole programs built on this model. But things like GPUs are still using a shared memory type system if you end up programming for GPUs. Message passing, on the other hand, is a bit closer to how the supercomputer actually works, where you've got split up compute nodes, each doing their own thing, and then they're communicating over the network. So the memory is completely separate, so there has to be a communication step, which is taking data. If we're computing the red process here, it has to get this blue boundary data, this halo of values around its own area, and load that in so it can then find the values of neighbours and so forth. So rather than looping over the whole domain in distributed memory, we only ever loop over that single process's values. So again, we're going over columns first, just to make sure we're looping in the correct order for Fortran. Since all of the memory is kept separate, you don't have to worry so much about different processes writing to the same area of data. There's less chance for conflicts. The techniques of shared and distributed memory can be combined as well. So you can have shared memory within a single node, so there's multiple cores in a single node sharing memory, and then those individual nodes can communicate with each other using message passing. That's sort of making the best use of the supercomputer. Coupled climate models, such as those used in the CMIP experiments, consist of several component models. So we've got atmosphere, land, sea ice, and ocean, all set up to talk to each other. So they do this by using what's called a coupling program. And that's taking fields from, say, the ocean, say the sea surface temperature, and sending them into the sea ice and sending them into the atmosphere, so that each of the programs, they've got feedback between each other with their model fields. And equally the other way, so we might get radiation fluxes coming from the atmosphere to the land or to the sea ice. The main complexity here for coupled models is making sure that these fields are compatible, so that they're in the same units and you've actually got the correct variable. The definition of one model matches the definition of the other. It also has to convert the grids. So you can see at the top we've got our atmosphere grid, which is just a normal, that long grid. And here we've got the tripolar ocean grid, where we can see that the Asia goes up to the top and North America goes up to the top. So it's a bit distorted, so we have to interpolate between these. So access, this is a representation of the access CMIP model. The component models are joined using a program called Oasis, and that automatically handles all of this interpolation for us. And when fields get sent from the atmosphere to the ocean grid, it gets automatically interpolated by this program. So it doesn't all have to go through the coupler. There are other ways to couple two models. So for instance, in Access, the cable model is a library that gets called by the atmosphere. Since they're running on the same grid, it's much easier to directly pass values into the land model. The land model also, because of the way it's built, doesn't communicate with the other processes. Each land cell is fairly independent of each other. So that's a method called tight coupling, where we've got them directly written into each other. Or there's a looser coupling going via a more generic coupling program. Even with all of the variables being correct and with the grids being converted, developing a coupled model is still really complex because there's a lot of tuning involved in testing that the models are stable when they're connected to each other, that the feedbacks aren't too large and causing the whole thing to crash. So we've got a lot of processes doing the work for us. So how can we efficiently make use of that resource of the supercomputer? So first looking at I/O. So that's reading data from or writing data to files. That's always going to be much slower than reading data from memory if you've got it stored, or doing computations on that data in memory. So there's a few ways that we could do this. The most obvious way is to have all of the data sent from all of our processes to a single process, which is normally called the root process, and that writes out our output file. That's kind of inefficient because there's a lot of time spent in sending all of this data and receiving it, and then writing, while this root process is writing out the output file, the other processes are basically sitting around doing nothing, and that's wasting our computer time. But models can also use different strategies. Similar to how we parallelize our computations, we can parallelize the output. So we can have each of our processes, each writing out their own bit of the output file, and then we can stitch them together later as a post-processing step. So that's the method that's used by the Malma-Ocean model. Raijin uses a special file system called Bluster that's designed for supercomputers, which makes this really fast. It allows you to write lots of files at the same time and splits up the files onto multiple storage nodes. Another way to do it is to have specialist I/O processes. Their only job is to deal with writing out data. So we can send data to our I/O process and it can write out its output file, but the compute processes can keep going because they don't have to wait for that one I/O process to completely write out its file. So that's a method used by WRF and the UM. So a bit about scaling. Supercomputer time isn't unlimited. There's a lot of people using NCI, so we want to make sure our models run as efficiently as possible. We can make our run faster by adding in more parallelization, by adding more CPU cores, but not infinitely so. So what you find when you start to parallelize a program is you've got a bunch of parallel programs that as you add more programs, this parallel time decreases because the data is being split up finer, it takes less time to run. But you're always going to have some serial parts. So things like reading in inputs or writing outputs if you're just writing them out on the same process, or summing all of the values, things like that. So as we add more processes, the parallel time gets shorter and shorter, but the serial time tends to stay the same. So what you end up seeing is something like these curves, where increasing the number of processes and increasing the speed up, getting to enough processes and the speed up stops. Your compute time is dominated by those serial processes. So effectively, once we're up here, adding more processes is wasting those processes. They're not getting us our results any faster, and we're still spending our SU resources to compute the model. So we don't want to be up at this limit. We want to be in this optimal zone where adding more resources is actually effective. So the best way to discover where your specific model, because this is going to change depending on your model and indeed depending on the configuration of your model. So the best way to optimize this is experimentally. So just doing a short run. If your full run is running for 10 years, say just do a month. So just do a month run and see how much it costs, both in your SU cost, which you can find at the end of your log, and as well as wall time, So optimising the product of the SU cost and wall time tends to be the most efficient zone. You can, if you're low on SU for your project, you can decrease the number of SUs, which will slow your wall time. So that's the time you spent waiting for results, but lower the cost. Or if you need results really fast, you can talk to your other project members, because our SU resources are a shared resource between the members of your project. So you talk to them and see if you can increase the number of CPUs, which makes your job less efficient, but will get your results faster. If you're writing your own programs, it can be worthwhile to use a profiler. Profilers are tools which measure where your program is spending all of its time. So it can go through the lines in your program and print out a little graph of the program spent this time doing this function and this time doing this function. Or it can just give you a list of functions and where they're being run. So that's really useful for being able to spot the slow parts in either your model, or even if you're doing an analysis using compiled language like C or Fortran. So on the left here is an example of ARM map, which is one of the profiling programs that NCI have installed on Raijin. There's quite a number of different programs that specialise in different things. It's also common to run into bugs and errors when developing any program, and that's no less the case for climate models. Even if you're developing just your own science scheme, you might have bugs that crash the model. If you're developing your own program, it's helpful to add tests. So those are little programs that try running your function with sample inputs and checking that the outputs are correct. So that's really helpful when developing a new function. If you're starting up with a big full model and trying to work out why it's crashing, for instance, you can run it in a debugger, which lets you basically manually step through each line in your program and check the values of variables, see what your memory is looking like. So some debuggers are especially made for distributed memory programs. They let you switch between the different ranks of your process and see what the memory is on each of those ranks. So this is ARM's DGT debugger. The Total View debugger is also at NCI, also really good for doing this sort of thing. So we run climate models not just to spend all of our compute time that NCI give us, but also to do science. And for this, we need to get some sort of output from the model. So most models let you configure what fields you get output from the model and at what time. So if you want a daily field getting output or a monthly mean, what levels fields are getting output on. So it's important to be selective in what values you're requesting from your model, because storage space isn't unlimited. We are, as a centre, fairly full on our storage allocation. So it's important to only get the fields you need to be able to do your work, or if you're going to be publishing your work, obviously get those fields that you need for publication. This is especially important for high-resolution models. So we've got ocean models that are getting to a 1/10 of a degree resolution over the globe. Outputting at high resolution is going to fill our storage space really quick, especially if you're outputting lots of fields that you're not really going to look at. So we really encourage you to be efficient in what you're requesting. The ARC requires people funded by it to publish data used in their publication using FAIR principles. Data should be findable, accessible, interoperable, and reusable. So these principles are important for the data that you're creating in your work and sharing with the world via publication to actually be usable by other people. If you're just sending someone a text file of numbers with no clue about what the units are or any time series, that's really hard for someone to actually use, as you saw with the CO2 files for the practicals. So part of the work that the CMS team, that my group does in the centre, is making sure data produced by researchers within the centre is following these principles and is easily usable by other people. You can find data produced by the centre as well as other research groups in a variety of data catalogues, such as the NCI's GeoNetwork catalogue or the Research Data Australia catalogue. And the CMS team can help you get your data published to these areas. So yeah, more information about the FAIR principles and about how best to share your data is available from a group called the Australian Research Data Commons, which is funded by the ARC. As well, we obviously give advice if you send us an email asking for help with any data set that you're wanting to share or to publish as part of a paper that you're working on. So as part of these FAIR principles, we want our output data to have metadata which is describing the file's contents. For climate, we're pretty lucky. We mostly work with NetCDF files, which are a really good self-describing example of a self-describing data format. Other formats that you may come across include GRIB, which is used by weather forecasting centres primarily, and the fields file format that's used by the UK Met Office's model. These are less self-describing, so they don't have all of this metadata in them. You have to add them yourselves. So a NetCDF file contains a bunch of information about what its contents are. It has the size of variables. It has axes. So here's the time axis. It gives us a unit for what values they are. Information about the calendar type if you're using an alternate calendar, like a 360-day calendar. As well as for each variable, it gives a standard name. So standard names is important because that's a controlled vocabulary. Each file that's having some sort of temperature value will say the standard name is an air temperature. That makes tools able to read data from multiple different model types and work with that data easily. So any tool for working with air temperature data would be able to read this file. So also, in addition to per variable metadata, you also have global metadata. Things like where this data came from, who made it, do I have the rights to be able to use this data for my work, what's its license? There's a wide variety of tools for working with NetCDF data. Lots of them we've got installed on Raijin. Things like CDO, the climate data operators, and NCO, the NetCDF operators, that you grab a NetCDF file, do things like generate a climate mean, generate a climatology based on that file, just with a simple command. There's also languages, if you're doing something these don't support, for libraries for C, Fortran, Python. There's a few different Python libraries. My favourite's Xarray because it lets you work with the coordinate values instead of having to calculate offsets in arrays. So in addition to being able to read just a NetCDF file, all of these programs here are able to read data over the network using a service called OpenMP. Most published data sets, if you find a NetCDF data set from NOAA or whatever, will be served over an OpenMP server. You can feed an OpenMP URL directly into any of these tools, and it's able to show you what that data is without having to download the whole thing. So that saves a lot on network time. You don't have to sit there waiting for downloads before you can use it. Within the centre, we primarily use NCI, the National Computational Infrastructure in Canberra. This is really cool because the Raijin supercomputer they use is also used by CSIRO for big climate runs for CMIP6. It's also used by the Bureau's research centres. So that allows us to share data and model configurations between institutions really easily. It allows us to collaborate much more easily. So we really encourage you to use NCI if you're going to be doing supercomputing work. When Raijin debuted in 2013, it had about 60,000 Intel Sandy Bridge nodes and was in the top 30 fastest systems in the world. Over the years, it's had a couple upgrades to try and keep it up in the fastest computers in the world. On the top 100 list, there was 24,000 Broadwell cores added in 2017, and 6,000 Skylake cores added recently. And there's a number of specialty compute nodes as well that allow you to use things like GPUs or things like Xeon 5 processors, which are useful if you're really interested in the computational side of developing models. NCI's been given a grant of about $70 million to replace Raijin with a new machine. We're sort of expecting information on what exactly that's going to be soon. We were hoping for this week. They're claiming that it's going to be in the top 25 fastest supercomputers in the world when it's deployed. So judging from the current machine size, that's going to be 4 to 5 times the compute power of Raijin with more than 150,000 compute cores. So Raijin's got a bit of a heterogeneous nature because of all of these upgrades over the years. There's a bunch of Sandy Bridge cores, and the memory on each of these nodes varies from 2 gigabytes per node to 4 gigabytes to 8 gigabytes. If you've got a really big memory request, your job is going to run on these compute nodes here, which is a tiny fraction of the whole system. So try and make your memory request reasonable and accurate. A good rule of thumb is about 2 gigabytes per CPU, because then it can run on any of these compute nodes. So the more accurate you are in your resource estimation, the faster generally your job will start running. So similarly, there's a bunch of the Broadwell nodes and a few Skylake nodes. They're sort of a minority. Switching between these different node types can be inconvenient, but it can make your job run faster depending on who's using each of these. So these are all in separate queues, so how highly used a queue is will affect when your run starts running. So as you may recall, when we're logging into Raijin, we're put on one of the login nodes and have to submit a job to the queue. So you can run small jobs, things like compiling a program or previewing an output with an NC view on the login nodes from the command line. But the login nodes have limited resources, and there's a whole bunch of people wanting to run things on them. So if you try to run too big a program on one of the login nodes, it's going to be automatically killed by the supercomputer. Jobs that require more resources need to be submitted to the queue, which you do by creating a queue script. So this is a PBS job script header. PBSPro is the queue system used by NCI. So you create a script and you add these flags up the very top, which tell the queuing system which type of node you want to use. So normal is the Sandy Bridge, normal BW is the purple ones, and normal SL is the grey ones. The number of CPUs you want, the memory request. Remember, 2 gigabytes per CPU is a good rule of thumb. How long you expect to run, and as well as any other options for output and where it's going to start. If your job runs longer than 1 hour and you've requested 1 hour of wall time, it gets killed at the end of 1 hour, whether your job is finished or not. So try to be accurate with these resources. Same for memory. If you try and use more than 32 gigabytes of memory, your job will be killed and you won't get any output from it, unless you've saved an intermediate state. So there's a bunch of tools for working with queue jobs, which you can find more information about via NCI's help sites. Things like submitting a job. You can see all of your jobs or all of your project's jobs, as well as stopping jobs and seeing job outputs. If you've got an MPI program, one of those distributed memory type programs, the queue system automatically tells MPI run the number of processes that it needs to use based on your request. You don't have to additionally say, I need to run on 16 CPUs down here, which can be handy. So we've got a bunch of different types of queues. There's the normal queue, which is the default type of queue you want to use for standard big runs. If you're running a model for 100 years, you want to be running it on the normal queue. There's also the express queue, which is a higher priority job. Jobs submitted to the express queue will start quicker, but they're going to charge you 3 times the SU cost to be able to run this job. So it's fine for short jobs when you're debugging. For really long production jobs where you're going to be waiting a day anyway for the output, it's not worth that extra 3 times cost to get your run to start a bit faster. So there's also a slightly varying cost depending on which node type you're using. So these are all in SU. So an SU or service unit is what NCI uses to account for compute time on Raijin. 1 SU is basically 1 hour of 1 CPU. So if you've got a 6 CPU job running for 1 hour, it's going to cost 6 SU. If you've got a 6 CPU job running for 1 hour, it's still going to cost 6 CPU. One CPU job running for 6 hours, it's still going to take 6 CPUs. But that varies a bit depending on the queue type, as you see. So jobs are prioritised based on a number of factors, including the size of your request in memory and wall time and so forth. It needs to find an actual physical slot on the supercomputer where your job can run. How much of your project allocation is remaining. So each of you running on NCI will be part of a project which has some amount of SU that it can use for a calendar quarter. So if your project has been used more than its fair share, it will be deprioritised in favour of people who haven't used as much. So it's best to be as accurate as possible for things like wall time requests or memory requests without going over so much that your job gets killed. Because that makes it easier for the queue system to find a slot where your job can be run. So in addition to SU and processor power, you also need storage for your data. There's a bunch of different storage areas at NCI for different types of data. Your home space, that space is just for you. It's really, really small. You only get 2 gigabytes of data. It is backed up though. So if I go and delete my project's configuration scripts, for instance, and it was on my home, I can email NCI and ask them to recover that file for me. The rest of these, you don't get that. If you delete a file on short or G data or on tape, it is gone for good. There are no backups. So please be careful. Though, remember, if you've saved your model configuration, you can get that model output back just by running the model. So it's generally not the end of the world. So the other areas, the G-data, the short, have a shared quota, a shared allocation for all members of your project. So if you're a member of W35, you and all members of W35 count towards these allocation quotas. The short space is intended for short-term storage. Currently, there's no time limit on the files that are created here. When the new machine comes along, it's expected that there will be a time limit for how long files can sit on the short file system, after which they get deleted. G-data is for medium-term storage. It works pretty much similarly to the short file system. The really cool thing with G-data is you can access it from the cloud. So you can access it from things like the VDI system, where you can able to run Python scripts or MATLAB scripts inside the NCI cloud and still have access to data stored there. There's also tape. There's a lot of tape storage. Tape storage is cheap. It's slow though. So to store data on tape, a physical robot has to go through NCI and grab the correct tape and load it into the tape machine. So it's all automatic, but you have to wait. And there's a special command to access data stored on MDSS tape store. So you MDS put a file onto the tape store and MDS get a file back off of that tape store. Also, there's storage directly on the compute nodes, which you can use during a job. They have like a 400 gigabyte SSD on each of the compute nodes. They're separate on each compute node, so files saved on one compute node aren't visible from another compute node, and it disappears when the job's done. So it's useful for if you're doing an analysis as part of your job. You'll unzip your data onto this JobFS, do all your work on the data, save your data onto either short or G-data, because JobFS goes away at the end of the job. You also have to make a special request if you're going to use this storage. So you have to use back in our PBS thing, we have to say -L JobFS equals 100 gigabytes or whatever added to here to be able to use that storage. To encourage publication of data, we've got some special project areas with extra quota specifically for published data. So there's data published by users of NCI on these project systems. There's also a wide variety of data sets that NCI mirror locally for us as users, so that we can use these data sets without having to go and download them ourselves and fill up our storage with, say, 5 petabytes of ERA 5. So we've got things like reanalyses, big stuff like the ECMWF reanalyses, smaller stuff like the OSTIA SSTs, wide variety of the CMIP 5 publications and CMIP 6 as they're being produced, of course, coming onto Raijin, a bunch of rainfall products, things like that. You can see the full list of data sets by going to the Climate CMS wiki. And we've got a big page with all of the different data sets that you can find at NCI. If there's a data set that you want access to that you think is going to be useful by other people in the centre, let us know. Email us and we'll get that data downloaded centrally onto these central data set stores where they're not taking up space in the CLEX quota allocation. They're stored instead centrally at NCI. Just email us if there's something you're interested in, or if you spot an error, or if there's a variable missing from one of these that you'd like to use. So fairly recent development at NCI is the cloud computing system. This is a system called Tenjin, which is used to run the VDI, amongst other things. It's also pretty cool for developing outreach and visualization tools. So things like modelevaluation.org is a system developed by researchers in the centre. It's loading data from the G-data file system, running some processing on it to compare the results of different models, all on the NCI cloud. So most of you here are affiliated with CLEX. So we have resources at NCI that we're able to use. We've got a bunch of allocation that NCI give to us as the flagship C project. So individual researchers, any Australian researcher can submit a merit allocation proposal to NCI and get some amount of time. The centre as a whole, outside of that system, gets allocation from NCI. We've got about 3.1 million SU per quarter, so that's quite a lot. We've got about 0.4 petabytes of storage on tape, on G-data, and a lot of storage on tape as well, 0.75 terabytes. And that's split between a number of projects at NCI. So we've got things like extratropical variability, uses a lot of the compute time for their high-resolution ocean runs, rainfall, drought, tropical variability, and heat waves. So we've got a bunch of different projects at NCI, 6 projects for the general computing stuff, as well as a bunch of data projects. So any member of CLEX can request to be a member of the appropriate project. Excuse me. If you're just using a small number of SU for a quarter, if you're using under 1,000 or so, no worries, that's fine. If you're going to be doing larger model runs, we do ask you to communicate with the other members of your project just to make sure that we have enough compute resource, SU resource, for everyone to be able to do their runs during a quarter. So allocations at NCI are quarterly. At the end of a quarter, all of the usage goes back down to 0, and we can start running again. We are able to shift around allocations between these projects fairly easily. If you've got a merit allocation project as well, we ask that you use that in addition to the CLEX Resources, just to make sure things are balanced. If your project runs out of SU allocation, so if you run out of time in the computer before the quarter ends, it's not the end of the world. They go into a special bonus queue. So they'll be low priority, the lowest priority in fact. But if there is spare space overnight or something where Raijin would otherwise sit idle, it will run your jobs. So things can still get through. There's a bunch of tools at NCI for seeing your allocations and how that allocation is being used by individual project members. NCI account is an overall view, and the short files report or G-data 1 files report and so on will show per user disk usage. We've also got some tools we've developed ourselves in the CMS team, things like NCI Monitor, which will produce a graph for each user of how they've used storage over time, which helps for some of the administration people if you end up helping with administrating a project. We also develop things for better managing the storage and other resources at NCI, things like NC Compress, which will go through a directory tree and compress any NetCDF files that it found, so that you can still use the data, it's just taking up less space. Final slide. So I'm part of the CLEX CMS team. We provide support to researchers at the centre in using the NCI systems, in publishing data, analysing data. So we've got team members at each of the centre's nodes. In fact, we're all here today, if you'd like to come up. So this mob is who questions sent to the CWS help get sent to. So we've got Aidan at ANU, Danny's at UNSW, Paula UTAS, Holger Monash, Claire at ANU. So yeah, you're welcome to come and talk to any of us if you've got a problem with running a model, with doing data analysis, accessing data. If you've got a Python bug that you just can't work out, come to us rather than spending weeks of your precious PhD time trying to debug something. By all means, have a go. Take a couple of days. We're here to accelerate your research. We're here to unblock those blockers where you've got a bug that you just can't work out. We've got a wiki there. Melissa's going to make all of these slides available afterwards if you want to take the links later. That's got a lot of information about what's at NCI, the models that we run within the centre, the data sets we have available. We run a weekly training session on each Wednesday. You can find more information on the Wiki's training page to find dates and a mailing list that you can join for notifications about that. We welcome any suggestions you have on what would be a cool topic to take a look at as part of these training sessions. We've also got a help desk at NCI where you can send emails to. That goes to us as well as some of the support staff from CSIRO and the Bureau for helping with the access modelling system and the various models that we use. We've got a Slack. If you like text chat, you can join our Slack. Anyone with a centre university email address should be able to join that automatically. If that doesn't work, send us an email over the help desk. NCI also have their own wiki with a huge amount of useful information on using their systems and parallel programming, things like the software they have available, stuff like that. We at the Climate Help Desk, we're not funded by NCI. We don't have any special access to their systems, so we are not able to reset your passwords or recover backups. Things like that, send an email to NCI via their NCI help desk. But stuff like Python, the Conda environment's maintained by us, so you're welcome to send requests for the new Conda stuff to us. Climate models, data, things like that, send them to us by all means. So thank you, everyone.